In this lecture, I will talk about fast Fourier transform. In particularly, we will talk about the companion node observation. Let's take a look at the companion node observation. If you remember in my previous lecture when I show you figure 2, where we have the data point capital N is equal to 16. And because we always want to express the number of data point capital N in terms of 2 raised to a certain power r. So in order to have capital N equal to 16, the power r must be equal to 4. And because r equal to 4, that telling us that in order to compute the unknown vector c theta, we need to compute 4 intermediate vector corresponding to level L equal to 1, 2, blah, 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 up to R, which is equal to 4 in this case. If you observe figure 2 in the previous lecture, which I will show you again in here in a minute, we can see that there are always we can always find 2 companion node that came from the same pair of node in the previous vector. So for example, as I will show you on the next slide, if you want to compute the vector f10 component and f18 corresponding to level L equal to 1, right? F1 means level L equal to 1. The computation of f10 and f18 both will require the data from the previous vector, which is called f0 and f8. Similarly, if you want to compute, let's say, in the level 2, L equal to 2, okay? If we want to compute the vector f28 and vector component f212 in level 2, L equal to 2, the computation of f28 and f212 in level 2 will require the pair of node data information about f18 and f112 in the previous level, which is level 1. So let's take a look at figure 2 again so that you can understand easier. So this is the same figure 2 that we talked to you earlier, assuming, like I told you before, capital N is equal to 16, and that implies that the power R must be equal to 4. And because of that, we need to compute 4 intermediate vector, which is called vector f1 correspond to level 1, vector f2 correspond to level 2, vector f3, and vector f4. Now, according to the previous slide, what did we say? What we say is, if you want to compute f10 and f18 in level 1, we need to have the data from the previous vector, which is called f0 and f8. Well, let's take a look in here. So as you can see, if you want to compute f10, which is this fellow, and f18, which is this guy right here, we need to have a pair of data at the same location in the previous vector, which means we need to have f0 and f8. Now, again, go back to the previous slide. We also say that if we want to compute the value of f28 and f212 corresponding to level 2, we have to refer to the previous data at the same location, which is f18 and f112. Now let's see, what does that mean in this figure? Well, as you can see, F18 if you want to compute F18, I mean F28 if you want to compute F28, which is this guy, F28, and you want to compute F212 in level 2, right? The data you need will be the previous data at the same location. That means to compute F28 and F212, we need to use the data of F18 and also F112. Okay? So that is basically, I just want to show you the statement in here can be verified by referring to the graph shown in figure 2. Okay, now let's go on to the next slide. We notice that the computation of the companion node are independent of the other node within the same level L vector. And what it means is, after you compute the value for F10 and F18 corresponding to level 1, we can override the value of F10 and F18. You can override that on the location F0 and F8. Now, to see that is true, let's refer back to the figure 2 again. So F10, F18. All right, let's see. As you can see, when you after you compute F10 and F18, obviously we need to make use of F0 and F8, F08. Now, after we compute F10 and F18, you can see clearly that the computation of the remaining term in the vector F1, such as F11 or F12 or F13 or any other remaining term, those computations of the remaining term have nothing to do with F00 or F08. It only requires the data for F01, F02, F03, and so on, but they don't need the data for F00 and F08 anymore. So for that reason, what we said is, as soon as you compute F10, the value F10 will be override in this location. After you compute F18, we got the value override this value. That's what it says. Similarly, after you compute, let's say, F28 and F212, we can override the value. We can store the value F28, F212. We can override it at the location of the previous vector F18, F112. So again, go back to the figure 2 and look at F28 and F212. Okay. If you look at level 2, let's say we want to compute F28. To compute F28, we need to make use of F18 data and also F112 data. And you can see clearly through the arrow indication here. You can see that. However, at the same time, when you come to calculate F212, you also need to refer to the same data, F18 and F112, as can be seen through the arrow indicate here and there. So after we calculate F28 and F212, you can see that the value for F18 and the data for F112 is no longer required or needed in the calculation for the remaining term of the vector f2. So for that reason, what we say is, as soon as we calculate f28, we will override their value on f18. As soon as we calculate f212, we will override it on f112. So this way, when you propagate the procedure to the last step, you just keep override the vector f3, override the vector f2, and vector f4 you override on vector f3. So at the end of the procedure, you don't need any additional computer memory, because whatever the vector that you have initially, which is a vector f0, you just keep override it by vector f1, and then after that vector f2 will override on top of f1, vector f3 will override on top of f2, and vector f4 will override on top of f3. So that means we don't have to create any new additional array, and that will save a lot of computer memory as well. So